Here, the paper, that is the theory paper is real analysis colon calculus 2 for the second semester of the mathematics. Here there are four chapters. First one is the sequences, second one is the inference series, third one unit number 3, unit functions of 2 and 3 variables. Fourth one is the integral calculus. Fourth one is the integral calculus. Here the allotted the, the units for me are first one is the sequences, second one is the series. I am taking unit 1 as well as unit 2. We are already started with the sequences. You see here, we are already started with sequences, and there are already studied sequence, and I think already you know the particles is also there. Here the particles are the 12 particles are these are the particles. Examine the convergence of the sequences. Example on limit 1 plus 1 by n to the power n as entire is equal to e. Verification of exponential series, verification of logarithmic, etc. Okay, these are the particles. Okay, now we are dealing with the theory here. Out of the 4 units, that is unit 1, unit 2, unit 3, unit 4, I'm taking unit 1 as well as unit 2. I'm taking unit 1 as well as unit 2. Okay, now here in sequences, here in sequences, the unit 1 sequences, the sequences of real numbers. Already I studied the definition of the sequence. It is a function from the set of natural number numbers to a set of real numbers. Real sequence means it is a function from the set of natural numbers to the real numbers, and is denoted by f from n to r, x from n to r, or a from n to r. And they are denoted by a1, a2, a3, a4, so on, an, so on. A1 is the first term, a2 is the second term, a3 is the third term, an is the nth term, an is the nth term. And here the power bracket, that is the notation for the sequence is sequence power bracket you have write with an or arrow bracket an. These two are here you are using only the power bracket with an you are using here. And here you see a1, a2, a3 are called the first term, second term, third term, or first element, second element, third element, etc. You are calling. And an is called nth term. Okay, and then you have to study the sequence that is containing the range of the sequence. Range of the sequence means that the set of the distinct elements of the sequence is called its range without repetition on which regarding to the position of the term. And here you see to take some sequence n equal to k for n of the n belongs to n, then you are getting here n equal to k, you are getting here. That is called the singleton set. The range equal to set containing the element k, that is called the singleton set. What is singleton set means? The set containing a single element is called singleton set. And already you see in case of representing that is the examples of sequences. In some of the cases, you are going to write in terms of the term containing, and that is the general term you are writing. And already you know the difference between the general term and the specific term. If you substitute the value in general term n equal to 1, 2, 3, so on, of course, because n is a set of natural numbers. So that means you can write here n 1, 2, 3, 4, and here you will get the first element, second element, third element, etc. And it is not true for all the cases. Either you can represent, if it is possible to represent in terms of when you can represent, otherwise you can write without the general one you can write here. You see here we are writing here. Here 1, 2, 3, 4, 1, 2, 3, 4, 5, 5, so on, 5, so on, 5, 5, so on, are writing here. That means A1 equal to A2 equal to A3 equal to A4 equal to 4. Already you know A1 means the first element, A2 means the second element, A3 means the third element, that is A4 is the fourth one. Now you can write here the sequence as n equal to 5 for every n greater equal to 5 current. It is not possible here to write in terms of n. And already you know the bounded sequences. What is bounded above sequence, bounded below sequence, and bounded sequence? Bounded above means n is less than equal to m, and here bounded below sequence is n is greater equal to m. If you club those two, you get here the bounded sequence. That is m less than equal to an less than equal to m, then that will be called as the range of the sequence is bounded, and you can say that the sequence is a bounded sequence. You see this A and the term here, okay. an is having bounded above an less than or equal to m and an less than or equal to m, you can say that is the sequence is bounded. Okay, unbounded means there is not bounded above, that is the unbounded sequence, and there are written unbounded above, unbounded below. Okay, then you are taking some of the examples, and then here you see you are getting here every constant sequence is bounded. It is also one of the case. And then here you see these upper bound supremum we are taken, greater lower bound infimum we are taken, that is a less than or equal to m, and any m number less than m cannot be a upper bound of sequence a. And then one more we are taken here, the real number m is set to the here b are greater lower bound or infimum. The sequence a n is here n is a bounded below sequence, and you can say m is the lowest bound of the sequence a, and you can add a greater than or equal to m, and any number greater than m cannot be a lower bound of the sequence a. And that is the case in case of maximum or greater lower bound. And we have taken some of the examples of maximum and minimum. Now already we have taken the limit of the sequence also. You see that is the definition limit a and n is equal to L. Then you can say that the limit of the sequence where a is the term with difference a is the term. Okay. Now here you can further taken some examples, and here you see these examples are already taken. Some of the examples. Now here you see convergent, divergent, and oscillatory sequences. Convergent sequence means already you know limit an as n tends to equal to L, that will be called as, you see the L is a finite and unique. Then only you can say the sequence an is the convergent sequence. And then limit an as n tends to equal to plus infinity or minus infinity, then that will be called as divergent sequence. Now further the third type is there, that is first one is the convergent sequence, second one is the divergent sequence, third one is the oscillatory sequence. Here you see the oscillatory sequences. Okay, here you see the oscillatory sequences. Here, two types. There are two types of oscillatory sequences. And the first one is a bounded sequence does not converge is set to oscillate finite. This is the first case here. The first type, n equal to minus 1 to the 4 n is a bounded sequence, because you see in case of the examples you are taken, supremum is equal to 1 and minimum equal to minus 1 you got there. Or you can say, you can write this as minus 1 less than or equal to an less than or equal to 1 you can write. That's why you can say an is a bounded sequence, because we are writing in the form m less than or equal to an less than or equal to an. You see here in case of that what I taken in a bounded sequence, there you got here m less than or equal to a less than or equal to m, there you got the case. Okay, now and then you see you can verify here limit a to n as n tends to infinity equal to limit where a to n means a n already you know a n equal to minus 1 to the 4 n. A to n means wherever n is there, that is not replaced by 2n. That means we are getting here limit minus 1 to the 4 2n as n tends to infinity. Already you know what is 2n here, 2 into the terms containing the natural numbers. You get 2 into 1, 2 into 2, 2 into 4, that means you are getting even number. Even number means you see minus 1 square minus 1 to the power 4 minus 1 to the power 6, that is equal to 1 you can write. Because you see minus 1 to the power 6 means you can write minus 1 square to the power 3 you can write. Minus 1 to the power 4 means you can write minus 1 square to the power 2 you can write. Minus 1 square means if you are getting here the power is the even one, that's why you are getting here 1. And limit a to n plus 1 as n times will be equal to, you are writing here wherever n is there, that you are replacing here in this by 2n plus 1, so that you are getting here minus 1. Because you see in case of the that is a to n plus limit a n as n times will be equal to, you see here you got a minus 1, because 2n plus 1 is the odd number, and all of them told you wherever the small letter n is, that belongs to natural number capital N. You can replace n by 1, 2, 3, so on. Whatever may be the value here, you are going to get the equal to minus 1, because you are getting here the power is the odd number. Okay. Now you see you are getting here, oh, that it's not convergence. Why it's not convergence means it must be, limit must be finite and unique. Limit an as n tends to be equal to finite and unique. But here you are getting two values. If you got two values, one of them you can say that is a unique one. That is the case here. Two values here. One you got here minus one you got, therefore is not convergent. And here already you got the bounded sequence. That's why you are writing here. Bounded sequence does not converge is said to oscillate finitely. Okay. Now one type is over. You see here the second type. Okay. Here the convergence is not obeyed here, and then here you see convergence case is not obeyed here, and then here you see This is a bounded sequence because you are writing in the form m less than or equal to a n less than or equal to m, that is equal to minus 1 less than or equal to a n less than or equal to 1 you are writing. Okay. Now the second type, gain an unbounded sequence does not diverge is set to oscillate infinitely. Is set to oscillate infinitely. Okay. Here if you see the sequence minus 1 to the 4 n into n. Here, this is equal to 4 bracket is how to write gn. The gn equal to what is the value? Minus 1 to the 4 n into n. This is the sequence that is the nth term you are writing here. Here also the same way, limit a to n. Wherever n is there, here in this case you are replaced by 2n. And here minus 1 to the 4 2n value is there. Already 2n is the we going to get the even number. That means with the plus 1 we are going to get plus 1 into 2n as n times infinity 2 into infinity we are going to get here the equal to infinity. Here also the same way, limit a to n plus 1 as n times is equal to limit wherever n is there we have to replace by 2n plus 1. You see the first case we are getting here minus 1 to the power 2n plus 1 is equal to minus 1 we are getting minus 1 into 2n plus 1 as n times infinity equal to minus 2n plus 1 as n times infinity under the limit that is equal to the right. If the difference n by infinity 2 into infinity plus 1 is equal to minus infinity we are getting here. Okay. That means you see here the sequence does not convert. You see the sequence does not diverge because you see in one case you are getting the infinity, in the other case you are getting minus infinity. Therefore, this is not divergent. Divergent. Okay. And then here you see the sequence oscillates infinitely. Okay. It oscillates between translated to minus infinity to plus infinity to minus infinity is oscillating. Okay, the sequence is not divert. Divert means you have to get here, here infinity, here also if you get plus infinity, you can say that is divergent. Or here if minus infinity, here also minus infinity, you can say that is the divergent case. But here you are getting one is the plus infinity, another one is the minus infinity. Therefore, the sequence does oscillates infinitely. Okay, the sequence oscillates infinitely. Now, the next sequence is null sequence. Null is itself says that there is no term. Here you see null is zero. Okay, you see here a sequence n is said to be null sequence converges to zero. That is limit n as n tends to be equal to zero. Then that will be called as a null sequence. Okay, and then you see the examples are 1 by, and if you take limit n as n tends to infinity, you get limit 1 by infinity as n tends to infinity under the limit we're going to get 1 by infinity is equal to 0. Here also the same case we're going to get here. Here also whatever the numerator here you're getting 1 by n is there here, you can write 1 by the power whatever may be here, the numerator is you are getting here infinity as n tends to we're going to get 0. These are the three examples of getting to get for null sequence. Okay, so that you can write maybe more. Now the next one you see here, you see the syllabus there. There you got there you got every convergent sequence is bounded. Every convergent sequence bounded is there, and then one more is there. You see theorem number one. Every convergent sequence has a unique limit. Every convergent sequence has a unique limit. You see under the sequences you got here. Every convergent sequence has a unique limit. This is there for your syllabus. Your sequence cannot converge to more than one limit. Okay. That means the sequence is having only one finite and unique value. That's how to prove here. Okay. Now, if you take here in the proof, if possible, let's say sequence A converts to two distinct real numbers. Distinct is different. Okay. The real numbers L1 and L2, let epsilon equal to half of modulus of L1 minus L2. Since L1 is not equal to L2, modulus of L1 minus L2 greater than 0. So the epsilon equal to 0. This we have to write. Okay, we have to take two numbers L1 and L2 for the same limit of an. You are going to get the limit an value equal to as n is equal to L1 as well as L2. Now you see, according to the definition of the limit of the sequence, you can write here. Now the sequence A converges to L1. That implies, according to the definition, you can write given epsilon greater than 0, there exists a positive integer m1 such that modulus of n minus L1 less than epsilon by 2 for every n greater than or equal to m1. Okay. Similarly, you take the second one, that is L2 containing, that is the sequence A converges to L2. You see here, the sequence A converges to L2. Given epsilon greater than 0, there exists a positive integer m2 such that modulus of 8 minus L2 less than epsilon by 2 for every n greater than or equal to m. The difference is only the first case is equal to the second one. In case you have to replace L1 by L2, and here you have to replace by M1 by M2, so that you are going to get this. Now you say you take m equal to maximum of m1 comma m2, whichever is the maximum out of m1 and m2, you have to take is equal to m, how to take. Okay. After taking that, you write here. You write collectively by combining first and second. This one as well as this you have to combine. This is one and this is another. By combining those two, you can write modulus of a n minus l1 is less than epsilon by 2 and modulus of n minus l2 less than epsilon by 2 for every n greater than or equal to n. This is collectively you are writing, okay. Actually, in the first case you are writing here for every n greater than or equal to m1. In the second case you are writing for every n greater than or equal to m2. But here you are writing after taking m equal to maximum of m1 and m2. You are writing for every n greater than or equal to n. Now you consider modulus of L minus L1, L1 minus L2, which is equal to, you can rewrite this as L1 minus AN plus AN minus L2. If you take here, if you open the bracket here, minus AN plus AN will cancel, original will be written as it is, okay. Now the same you can write as, you put this in the bracket here also in the bracket, so that you can write less than or equal to L1 minus AN modulus sign plus AN minus L2 with the modulus sign. Because you know the properties of the modulus containing two components. You see modulus of x plus y is less than or equal to modulus of x plus modulus of y, you are writing. The same you are written here. Okay. X means this is y, the second component of x and y. That means you can write less than or equal to first component is modulus of x plus modulus of y means first one, second one. Okay, because modulus of x plus y is less than or equal to modulus of x plus modulus of y. Now, which is less than or equal to, you write the same thing as L1 minus AN, you can add as AN minus L1. If you take minus as common, and minus you can neglect and you can write here AN minus L1 and the second component as it is you are writing here. Now, you see here, you see this, the collectively you are written this less than epsilon by 2 here, AN minus L1, AN minus L2 is less than epsilon by 2. You write, replace the values AN minus L1 by epsilon by 2, by also epsilon by 2 equal to epsilon. If you add those two epsilon by 2, you are going to get 2 get chance to get epsilon for every n greater than or equal to m. Why you have to write this is epsilon means, you see according to the definition you have to prove the value is, that is modulus of L1 minus L2 is less than epsilon for every n greater than or equal to m. That we have to prove, because we have to get the definition. That's why you are writing here. The first one is the second one, we are adding and we are getting 2 epsilon by 2, 2 get cancelling, we are getting here epsilon. And now what we got here, modulus of L1 minus L2 is less than epsilon for every n greater than or equal to m. Now, it is a contradiction to our assumption that epsilon equal to half of modulus of L1 minus L2. Okay, this is, yeah, our assumption is false. That's why we are writing here L1 equal to L2. So they have taken different one, but here we are getting this is less than epsilon. Less than epsilon means there is absurd, that is not possible. There is a contradiction to the value epsilon equal to half into modulus of L1 minus L2. What we are taken at the starting, whatever we are taken at the starting, you see A minus L1, A minus L2 less than epsilon by 2, you got to say. Now, what we got here, there are not two limits are existing, they are unique and finite, and that's why you are writing here L1 equal to L2. Now, the next theorem, every convergent sequence is bounded. Every convergent sequence is bounded. Now, proof, let sequence A be a convergent sequence converging to N. That is what we can say. Limit En as n tends to equal to L, you can say, because N is a unique and finite one, okay, because A is a convergent sequence. Limit En as n tends to equal to, you can write L, which is unique and finite. Now, for epsilon equal to 1, there exists a positive integer m such that modulus of A minus L less than 1 for every n greater or equal to m. That means, you see, the epsilon value you are taking here 1 and you are writing the definition of the limit of the sequence and you are writing here modulus of this is less than 1 for every n greater or equal to n. Now the same you can write as here. The same you can write as here. Now already you know, if suppose modulus of x is less than y, you are writing minus y less than x less than y, you are writing. The same way here also you can write minus 1 less than modulus of a minus l less than 1, you can write. The minus 1 less than a n minus l less than 1, you can write. Now the same you can write as here, just to add L for the all the cases, all three components. You get here L minus 1 less than a n less than n plus 1 for every n greater or equal to n. Because just to take care, this is by using the definition you are writing here, okay. Because modulus of x less than y means you can write minus y less than x less than y. You can write for every n greater or equal to m you are writing. Now just to see here, let g equal to, that is smaller to g equal to minimum of a1 a2 so on to am minus 1 comma n minus 1. G equal to maximum of m1 a1 a2 so on to am minus 1 l plus 1 you are writing here. Okay, l plus 1. Now you can start directly here. G less than or equal to a less than or equal to g, because g is the minimum one and capital G is the maximum one. That's why we are writing here g less than or equal to a less than or equal to g for every n belongs to n. Therefore, the sequence n is said to be a bounded sequence, because you see in the format what you got in the text, you see there, if you got m less than or equal to a n less than or equal to m, one is the first one is the small letter, second one is the capital letter you are adding. Okay, that's why you are adding an is a bounded sequence, because this is bounded above as well as bounded below. Here is g less than or equal to a, you can write as a less than or equal to g, an greater than or equal to g, and an is less than or equal to a greater than or equal to g means an greater than or equal to g means that's the bounded above sequence. An less than or equal to capital G means you can say bounded below sequence. Bounded above as well as bounded below, therefore it is a bounded sequence. The converse of the above theorem is not true. The converse in the sense you see the sequence is bounded, then that need not be a convergent. Sequence may be bounded, but the sequence, but that is not necessary to be become a convergent. Now just to see here, you take some, and the time you take here a n equal to minus 1 to the 4n. Of course, so sequence a n is a equal to minus 1 to the 4n in the sequence. N equal to minus 1 to the 4n. This sequence is bounded. Is it not? Already we are discussed in case of the oscillator sequences. Minus 1 to the 4n is a sequence which is bounded, and the infimum is minus 1 and supremum is plus 1. Or the infimum in the sense greatest square bond, supremum in the sense lowest upper bound. But this is not convergent. We refer that example what was taken in case of the oscillator sequences were taken there. Okay, and then we can say boundedness is a necessary condition for the convergence of the sequence. Okay, if the sequence is convergent, means that definitely it will be a bounded sequence. If the sequence is not bounded, it cannot be convergent. Okay, that reverse is not allowed here. That is, now, for example, consider the sequence n is not convergent, but it is unbounded. Then we say the sequence n is not convergent, because you see limit an as entire simply equal to, we are going to get divergent case, not the convergent, but it is unbounded. Unbounded means it is not bounded above, it is not bounded, that is, it is not bounded above as well as bounded below. Now, here you take limit an, the third theorem, limit an, if you limit an as n is equal to L, limit modulus of an as n is equal to modulus of A. Now, you take the definition again, limit an as n is equal to L, that's the limit of the sequence you are writing here, given epsilon greater than 0, the recognition positive integer m such that modulus of a must l less than epsilon for every n greater than or equal to m. Just now what we taken the definition of adding here. Now this is the problem. You see, we write here modulus of a minus modulus of l is less than or equal to modulus of a minus l. This just you remember this property. Okay, modulus of x minus y is modulus of x minus y is less than or equal to, or you write modulus of x minus modulus of y is less than or equal to modulus of x minus y, you can write. Now the same you can add as here, the right hand side modulus of a minus l is less than epsilon for every n greater than or equal to m. Therefore here you can write the same. You see, this is again using the limit of the sequence, you can write limit modulus of p n as n is equal to modulus of l. Modulus of L. Now the sequence modulus of A n is converges to modulus of L. Okay, that is okay. This is the main thing. You see, modulus of x minus modulus of y is less than or equal to modulus of x minus y. This is the main thing. And the remaining thing it follows as it is here. Okay, that is according to the definition of the limit of the sequence. Okay, definition of the converse of the above theorem is not true. What is the converse here? Limit of modulus of a equal to modulus of L, then it need not be limit a n equal to L. Okay, that is not convergent. Okay, if you take here, you are taking a n equal to minus 1 to the 4 n, modulus of n equal to 1 you are getting, because a n equal to minus 1 to the 4 n means you take different values, 1 time 1 1 time minus 1 plus 1 minus 1 plus 1, it takes a value. If you take a modulus for each the compound, you get here 1 is a constant, only one value. Minus 1, if you take a modulus, you get here 1. Therefore, it's a constant sequence. Modulus of n equal to 1 is a constant sequence. Of the sequence modulus of an converges to 1, but the sequence an is not convergent. Because you see an is not convergent, you see again here to go for the what are taken the oscillator sequence. This is not a convergent. Of course, this is a bounded sequence. This is a bounded sequence. Okay. Now algebra of sequences. Now algebra. Now after this studied bounded and unbounded sequences, convergent, divergent, and oscillator sequences are over. Then theorems on sequences. Every convergent sequence has unique limit is over. If modulus of its n, don't get confused here. Whether you write model that is the sequence xn or sequence an, you can write the notations xn, an, fn, you can write. Modulus of xn converges to L, modulus of xn converges to modulus of L. Every convergent sequence is bounded, that is over. Now, the next case we are going to discuss is the algebra of sequences. Algebra of, algebra of sequences. Yes, there are four cases are there. Okay, algebra of sequence in the sense sum, difference, product, and quotient of two convergent sequences convergent. You see the syllabus there you got here. This is the case. Bounded, unbounded are over. Convergent, divergent, oscillator is over. Monotonic sequence that we will discuss later onwards. Theorems on sequences. Every convergent sequence has unique is over. Modulus of xn converges to L, then modulus of xn converges to modulus. Just now you are taken there. There you are taken in model here. An you are taken here. So you can replace an by xn or you can answer the method. Every convergent sequence is bounded. That is also you are taken. Okay. Now here you got some difference product and quotient of two convergent sequences bounded that we are discussing. Sum means plus, difference means minus, product means into, and quotient means you have to divide. That is the case. Okay. Now here we will see algebra of sequences. See algebra of. Okay. Algebra of sequences. If the statement is limit if limit an as n tends to equal to a and limit bn as n tends to equal to b, then the first one limit an plus bn as n tends to equal to a plus b, and then limit an minus bn as n tends to equal to a minus b, limit an bn as n tends to equal to ab, and then limit an by bn as n tends to equal to a by b where b is not equal to c. These are the four cases. This is the addition, or that is the sum, and this is the difference, and this is the product, and this is the quotient of the convergent sequences. You see, an is a convergent sequence, a is a finite and unique, bn is a convergent sequence, and here the value of b is finite and unique. By using these two convergent sequences, we have to prove one by one these for how to prove here. Now we will see the first one, that is the limit an plus bn as n tends to equal to a plus b, that we will see here. Okay. Now this is also according to the definition. You have to know the limit of the sequence, then only you can add this. Okay, you have to be thorough with the limit of the sequence. Just now you have taken there in the previous case, refer that limit of the sequence means how you are writing there. Limit an as n tends to equal to L, then for a given epsilon greater than 0, there is a positive integer m such that such that you are writing modulus of a minus L less than m plus less than m for every n greater than equal to m you are writing. You see that here for n greater than equal to m. Now you see here let epsilon greater than 0 be given. Limit an as n tends to be equal to a. This is already given here. You see this is the given one. By using this, then if p then q, that you have to prove here. That is the p P is there, then you have to prove by using P, Q you have to prove. Okay. Now let epsilon greater than 0 be given. Since limit En as antacid equal to A, limit Bn as antacid equal to B, they exist positive integers m1 and m2 such that modulus of A minus A minus A less than epsilon by 2 for every n greater than or equal to m1 and Bn minus B with modulus sign is less than epsilon by 2 for every n greater than or equal to m2. Okay, that is the case. Okay. Now, just to see, already I've seen that what I've taken in case of that the limit of the sequence you are taken only m there you are taken, but here you are writing m1. Similarly, here also is another one you can take equal to m2 limit Bn there is a positive integer m2 such that modulus of Bn minus B is less than epsilon by 2. And here just now, here you are taking epsilon instead of epsilon, you are taking here epsilon by 2. Here also you are taking here epsilon by 2. And here instead of m1, you are writing m2, or you are writing instead of m, you are writing m1, and instead of m, you are writing m2. Now, the same case, what are taken the limit of the converted, what are taken that sequence, you are taken there, you see that. That is, every convergent sequence has unique limit that you are already taken. The same you are adding here. You see, every convergent sequence has a unique limit. Theorem number one you see there. Same you are written here. Okay, here you see theorem number one. This is the same you are going to apply here. You are written as a different component, but you are writing here there collectively. That is the case. Okay, same you are writing here. Now here this is the case. You are writing collectively, that is the case. Both are one and the same. Okay. And M equal to maximum of your taking and is the same A minus A is less than epsilon by 2, B n minus B modulus is less than epsilon by 2 for every n greater than or equal to M. Here also you are writing here A n plus B n minus A plus B with modulus sign is equal to, because you have to get limit A n plus B n as n tends to equal to A plus B. You see in the previous case limit A n as n tends to equal to, how to get A means you are writing here A n minus A the modulus you are writing. The same way here also you are writing here A plus Bn minus A plus B modulus equal to An minus A plus Bn minus B you are writing. Just you are here and you are writing, which is less than or equal to modulus of An minus A plus modulus of Bn, because you see modulus of x plus y is less than or equal to modulus of x plus modulus of y. The what same concept we are using, the convergence sequence has unique limit. Now replace this by epsilon bar 2, here also this by epsilon bar 2 equal to epsilon. Okay, if you add, you get here, this is less than epsilon by 2, because you see, here you got this is the main thing. Collectively, you are written here. This is you are using here. This is the case you are using. And here you are writing epsilon by 2 plus epsilon by 2 equal to epsilon for n greater than or equal to m. Now, what we got here? Limit of this is less than epsilon for every n greater than or equal to m, which implies limit a n plus b n as n tends to equal to a plus b. Okay, this is according to the definition. Just like an minus L with modulus is less than epsilon for every n greater than or equal to m you are writing. Limit an as n tends to equal to L you are writing. So same way here also you are written the same just by using the definition of the limit of the sequence. Okay. Now the converse is not true. The converse is not true. That means limit an plus bn as n tends to infinity does not necessarily imply two limits limit an limit bn. See here, an equal to n is there, bn equal to minus n is there. Both the sequences are divergent, because you see how you are seeing that is divergent. Limit an as n tends to equal to, going equal to plus infinity. Limit bn as n tends to equal to minus infinity. One time you are getting plus infinity, other time you are getting minus infinity. That means that is the sequence are divergent. Okay, you see an equal to infinity means you are right, limit an is infinity, limit bn is minus infinity. The sequence are both the sequence are divergent. But a plus bn, if you take that is equal to 0, you are getting what is 0 here? That is a null sequence. You see here, you are getting here an plus 0. 0 means a plus bn as a time equal to 0 is existing. That is convergent case you are getting here. Here, convergent case, because you see the converse of the theorem is limit